Okay, so I'm going to be talking about part of this pathway to predictability from the slow components of the in the ocean to regional climate, looking both locally in the response to SST and the remote connections. And I'll do that in the context of AG temp simulations, in particular the 5 models I've listed there. So this is kind of the bottom line in terms of interannual variability, where we expect SSTs to have an impact on temperature and precipitation. And if you note, the contour intervals differ by a factor of 2. So temperature has a greater signal coming from SST. And there's nothing too surprising here. We've seen this before. It's largely in the tropics, but there are regions in the exotropics that do have some controls by SST. I'll just look at just a few regions in a little more detail to look at the connection. So on the left is kind of the consensus correlation between the precipitation in those regions outlined in green and SST everywhere. Again, this is interannual. And on the right is, so that's based on 60 ensemble members from all these GCMs. And on the right is what the observation, so a single ensemble member shows you. And without getting into the details, things look actually pretty good, and especially in the Americas, the connections look really pretty good. There are some differences, certainly when we get into regions like the East Asia, where there are differences, but again, it's not clear how strong that connection should be, given that the left is this ensemble of 60 ensemble members, and the right is just one single ensemble member. So I'm going to look a little bit more at the direct response to SST. So what this shows is the different models and the precipitation variability, again, all annual mean conditions. And you can see the models disagree quite a bit, ranging from where the GEOS 5 model, for example, has rather weak variance to much stronger variance in ECAM 5. And at the bottom is the same quantity from observations from GPCP, suggesting that actually the weaker variability is perhaps closer to reality, though GPCP may also have some problems with the magnitude of the precipitation variability there. So for the model, then we can divide things up into the forced and internal component of that variance, and you can see again that there's quite a bit, the models differ quite a bit on how much of the variability is directly forced by SST versus what's internal to the atmosphere. And that has very important implications, of course, for predictability at in the different regions. One note is if you look at the fraction of the variance, they're not that different. They're still quite a bit different. I'll go into that more, but the models that have the strongest SST forced response also tend to have the strongest internal variability. So there seems to be some compensation there. So I'm going to look a little bit more now at the robustness of this regional connection to SST. Since we have 60 ensemble members, 12 from each, we can look individually at the connections, how robust they are. So this rather complicated set of plots is again revisiting these 4 different regions. And what the dots refer to is they're color-coded by the different models is how reproducible that response, SST response, is in these different ensemble members. So if you look at the upper left, you see, for example, a lot of clustering indicating a very robust, all the ensemble members are basically giving you that same response both in precipitation and temperature. And if you go to the lower right, for example, there's a lot less agreement, so a lot less uncertainty in what that response should be in terms of both temperature and precipitation. But again, indicating a lot less robust response by region. And the other thing I want to point out here is the models disagree a lot on how robust that response should be. For example, if you look at the lower right again, and look, I circled the blue circle kind of encompasses all the purple dots, which is the GSF model, which thinks in this region, precipitation the response for precipitation is quite robust. Whereas if you look at the response for the green dots, which is CAM4, it's showing a lot less robustness in both the temperature and precipitation response. So this is an indication of a reflection of the fact that these models disagree very much on how robust that forcing to SST should be. So just to summarize the interannual part, In terms of the patterns of the connection with SST, it's pretty good. The models are realistic, and the sort of multi-model consensus product is pretty good. On the other hand, the models really do disagree on how robust that response should be. So the connection to SST it differs quite a bit, and that has a lot of implication for our estimates of uncertainty and predictability. And in particular, the different models span different parts of this uncertainty space, so that a consensus product is probably not very good because it's spanning the wrong part of the space or spanning too large of the space to make it a useful product. So now I'm going to switch gears and look at the decadal problem. I'll be looking at the differences between the first 15 and last 15 years of the last 3 decades. I'll look both at the mean differences as well as, since we have all these ensemble members, we can begin to look in a much more robust way at the changes in the tails of the distribution. In particular, we're looking at changes in extreme dry years, in the probability of extreme dry years. So again, this is now the bottom line for the decadal result for precipitation. If you look at the right, that's from observation showing this very kind of complicated change that has occurred over the last 30 years with drier conditions occurring over the southern part of the US and parts of South America and Asia, and a change to wetter conditions over northern South America, Australia, and regions over northern Eurasia. And on the left, upper left, is what the models, the consensus of what all the models are producing in response to SST over that time period. And you can see it's remarkably similar, that the models are really giving us a pretty good estimate of what's happened over the last 30 years with pretty much these main regions I pointed out being reproduced in the model. At the bottom, just as a way of assessing not only the mean differences, but the changes in the extremes. Just one example here where the color coding is such that the red is showing regions where there's an enhanced probability of extremely dry years. So not surprisingly, that coincides roughly with where the mean changes are also drier. And you can look throughout the world where things are largely consistent with what the mean changes are telling us. So what's controlling this? It's this large-scale response to the SST. On the right is what we get from observation, the changes in the height field. And on the left is again, this consensus product of what the models indicate what's happened over the last 30 years. So clearly, certainly not the same, which we really don't expect, because again, it's 60 ensemble members versus 1. But it's really telling us, the left is telling us what the SST force component is and the implications we just saw for regional precipitation changes. And we can look at each of the models separately and indicating this kind of a more zonally symmetric response is quite consistent among the different models. So now let's look a little bit more at the SST forcing, what's driving these changes. On the left is from observations. We can see the temperature SST changes, this sort of change associated with the PDO and the AMO. You can see that more directly in the lower left. There's a very dramatic transition that occurred in the late 90s between these two decadal modes of variability. On the right is actually some work we did several years ago as part of the US CLIVAR working group on drought, where we constructed these kind of artificial SST forcing fields based on the leading patterns of SST variability. And so we reconstructed a field which, looking now, it turns out to be rather similar to what actually occurred. And so we can look at the response to those idealized patterns to tell us a little bit more of what's driving those changes. And again, on the left is the result from the AGCM with observed SST forcing. On the right is the response to this idealized pattern. So certainly not exactly the same, but very clearly we're capturing the main modes of forcing in these modeled simulations. And we can now break things up into the different components, the impact of the Pacific, the Atlantic, and the trend. And you can see here that the response is largely driven by the Pacific pattern. And this is the impact on precipitation. Again, we reproduce a lot of the features we saw before, and now we can actually get a sense of what part of the ocean forcing is really responsible for what patterns. Again, it's largely the Pacific. There's a little bit different story when it comes to the response in the temperature field, where now the trend and the warm Atlantic are also playing a role. But again, the Pacific is playing a leading role in those changes. So for the decadal part, the models do reproduce a lot of the major changes that have occurred over the last 30 years. And this is associated with this large-scale, largely only symmetric response in the height and the circulation. And the relevant forcing is largely the Pacific with some contributions from the AMO. So as my last slide here, in terms of the challenges, I think the important thing is here we need to look separately at these different time scales. What's driving these changes on seasonal time scales? ENSO is clearly a big factor there, but the other oceans occasionally also play a role. Decadal time scales, it's the PDO, AMO, and other decadal changes that are playing a role, and of course the long-term changes associated with global warming. And a critical part is this unforced internal variability. We need to get that right if we really want to get good estimates of uncertainty and predictability. And that's associated with atmospheric variability, internal Rossby waves, as well as land feedbacks. And these can also contribute at the large scale. They're not just local. They can be hemispheric as well. So that's it.
Thank you so much. We have time for a couple of questions. Yes.
It turns out, this is something that I didn't have a chance to talk about, but in terms of the Pacific, it's at the edge of the warm pool. What models really care about in terms of this kind of Rossby wave large-scale response, it's really at the edge of the warm pool. That's all that matters. Almost nothing else matters in terms of the large-scale response.
Yes.
I have some question because the response of precipitation in the climate model is much bigger from the decadal variation than warming trend. Is that correct? But we cannot see the single file, like when they have the future projection, like kind of drought frequency has been very increasing or decreasing, increasing a lot as kind of similarly linear trend or non-linear trend. So like have you checked the decadal variation performance in the single file or future projection from global climate level?
Yeah, I haven't, I mean, obviously, a lot of people have looked at that in the IPCC runs. But I think the key thing is over the last 30 years, when it comes to precipitation changes, it's largely decadal driven, these decadal modes. On the other hand, when it comes to the temperature changes, global warming is playing a comparable role. In particular, over U.S. is hit by all three. It's global warming, it's the positive AMO and a negative PDO. So we're getting hit by warming from all three. But in terms of the precipitation, that's kind of the main driver.
And then now the decadal variation, kind of recent decade, there is a shift of their phase. Like
there's some indication.
Actually hit the top, and then PDO actually go to the negative, and then like, do you think about the change in terms of the SSD connection with the drought over the land?
I'm sorry, I didn't quite get that.
So like there is a kind of change, recent phase shift in terms of the decadal variation, like PDO, AMO. And then compared to early 1900, compared to 2000 early, the response is going to, like the land surface response to the decadal variation is similar to the early 1900 or 2000.
Yeah, I mean, I suspect it may be, I haven't looked at that, may be different simply because we're in a much warmer world right now that those kind of mechanisms the land in particular contributions may be in a different regime.
Great, thank you so much.